Hey guys, it's Miss Maneely, and I am going to create a series of video tutorials to help prepare you for the Algebra 2 midterm exam. Now the midterm is also referred to as the second quarter assessment, and it's going to include some things from the first marking period assessment that were commonly missed. So even though we've focused on polynomial functions, exponential, and log functions this marking period, there are some problems on the midterm that refer back to what we did with quadratic functions and complex numbers. I'm dividing the series of videos into 3 sections that correspond to the units instead of going in order of the numbers on the midterm review because I didn't want to go back and forth. I figured this way, if you need to review quadratics, you could watch the quadratic video and so forth. And so if you pay attention to the numbers associated with each unit, that might also help you when you're studying and looking in your notes for review materials. So I'm going to begin with Unit 2, which is quadratic functions and complex roots. This is something that we did at the end or towards the end of first marking period. I've indicated problems that you will be able to use a calculator on and problems that you won't be able to use a calculator on. So again, just like with the first marking period assessment, there is going to be a calculator and a non-calculator section to the exam. So the midterm review is in the order, is in pretty much the same order as the exam itself. There might be some problems that I rearranged just to fit on the page better, but it does kind of skip around. That's why I'm doing the videos in a different order. Okay, so we're going to start with quadratic functions. Notice problems number 5, 8, and 9, as well as 18, all correspond to what we did first marking period. 5, 8, and 9, you are not allowed to use a calculator, but in number 18 you can. So I'm going to do the first 3 without a calculator and remind you of some properties and formulas that you need to know for your exam. So in number 5, again, we're going to start at number 5. For each equation, you are asked to calculate the discriminant and then identify the number and the type of roots. What you might remember from the quadratic unit is that any quadratic equation can be solved using the quadratic formula, which is assuming that your equation is in standard form. Remember, standard form is ax squared plus bx plus c equals 0. So if your equation is in standard form, then you can solve any quadratic equation using the quadratic formula, which basically just refers to the coefficients a, b, and c, and x would equal the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. That is the quadratic formula. But if we zero in on the quantity that's underneath the square root, if we just look at this quantity right here, that is called the discriminant. And what's nice about this is if I compute just that quantity, I can determine how many roots there are going to be. I can also determine if they're going to be real or imaginary. Now, what we learned in the polynomial unit is that the degree of the polynomial, and quadratics are also polynomials, is going to tell us the number of roots. So all quadratic functions have 2 roots. But the discriminant will tell us whether or not they're real or imaginary, and it'll also tell us if we have a double root. So if you remember, when the discriminant is positive, and this would be a good idea just to jot down on a piece of paper so that you remember to study these things. If the discriminant is positive, that means that there are 2 real roots. And what that means is there's going to be 2 x-intercepts on the graph. So if I were graphing, just above, if I were graphing the function, it's going to cross the x-axis twice. If the discriminant is 0, that means I have 1 real root, but it's a double root. And what that means is there's going to be a turning point on the x-axis. And so my x-intercept is actually going to be the vertex of the parabola, and that counts as a double root. And then if my discriminant is negative, that means I have 2 non-real or complex roots. And that means that my parabola is not going to cross the x-axis. So there's a turning point, but it doesn't occur on the x-axis. All right, so we're given two different equations, and we're asked to determine to calculate the discriminant and then identify the number and the type of roots. So in the first one, the equation is given to you in standard form. So the first thing I'm going to do is just identify the values of a, b, and c. So a is 3, b is my middle term, which is -6, and notice that I'm not including x. It's just the numbers themselves. And again, this is the non-calculator part of the exam. So to compute the discriminant, I want to do b squared. Let me write it again, b squared minus 4ac. Get in the habit, when you're dealing with b squared, to put the number in parentheses before you square it. So b is a -6. I want to square that, and then minus 4 times the value of a, which we said is 3, times c, which is 4. So if I think about -6, remember, anytime you square a number, it's going to come out positive. So -6, the quantity squared, is going to be 36. And if I multiply 4 times 3, that's going to give me 12. And 12 times 4 is going to be 48. And so I've got 36 minus 48. Now at this point, you don't even have to, well actually in this case you do have to calculate the discriminant. If all you are asked was to identify the number and type of roots, I can tell right away, even without subtracting, that my number is going to end up being negative. And if you do the subtraction, it's going to end up being a -12. And since the discriminant is negative, that means that there will be 2 complex roots. Okay. And it doesn't tell you what the solutions are. It just tells you the type of solutions you're going to have. If I wanted to actually solve the equation, I'd have to use the rest of the quadratic formula to solve. All right, in letter B, we've got x squared minus 6x equals -2x squared minus 3. Now this time the equation is not in standard form. So I need to get it in standard form by moving all of the terms to one side of the equation. Doesn't matter which side. I'm going to go ahead and just move everything to the left. I'm going to add 2x squared, and I'm going to move that to the other x squared over here. So notice that I'm just lining up my like terms. I also want to add the 3, and I'm going to do this all at once. So if I add 3, notice on the left side I don't have any constant values. So when I add 3, it's actually just going to kind of fit in next to the 6x. All right, so I've got x squared plus 2x squared. That leaves me with 3x squared. My -6x, there's nothing else in common, so it's going to stay -6x, and I have nothing to add to the 3, so that's going to stay +3. And then on my right-hand side, everything here cancels out to 0. So now my equation is in standard form. My value of A is 3, my value of B is -6, and the value of C is 3. So now when I calculate the discriminant, again, I'm going to want to make sure that I put my B term in parentheses, because it's going to be b squared minus 4 times my value of A times C. Okay, and again, when I'm squaring a negative, it's going to come out positive, so that's going to be 36. And this time I have 4 times 3, which is 12, and 12 times 3, which is 36. So I've got 36 minus 36. That's going to give me 0 as my discriminant, and that means that I have one real root. And if you want, you can indicate that it's a double. Okay, so that's how you use the discriminant to determine the number and type of roots. Okay, the next quadratic problem is number 8, and it deals with complex numbers. So remember, a complex number involves both a real and an imaginary number. So the real part tends to come first, and the imaginary part is second. And so typically, with a complex number, it's going to be of the form a plus bi, where a is my real number, and b is also a real number, but because it's next to an imaginary number I, that means that this is my real part, and this quantity here is my imaginary part. And together they make up a complex number. So even though we just learned about complex numbers this year, we've actually been dealing with complex numbers your entire life. Every real number alone is a complex number. So for example, the number 2 is a complex number. It's just got 0 as its imaginary part. So that's just a quick little lesson on complex numbers. We also learned that complex numbers have what we call a complex conjugate. And a complex conjugate is of the same form, except we're going to do a minus bi. And you're going to need both of those relationships in this problem. So in the first bullet, it asks, what is the complex conjugate of 2 minus 5i? Now notice when we're looking at the conjugate, the real number stays the same. The real part stays the same, but the complex or the imaginary term changes sign. So the complex conjugate of 2 minus 5i is going to be 2 plus 5i. And then it says to multiply 2 minus 5i times its conjugate. And this is a really important property in Algebra 2. If I multiply a complex number by its conjugate, something interesting happens. So some of you may be familiar with foiling. Some of you may feel more comfortable using the box method. I'm going to go ahead and use the box method because I think for those of you that struggle with FOIL, this is going to help kind of illustrate it a little bit better. It doesn't matter which term goes on the top or the side. You're going to put the 2, and then this I'm going to use as minus 5i. This will be 2, and the plus 5i. And then to fill in each of the boxes, we just multiply the sides that correspond to it. So in this first block, 2 times 2 is going to give me 4. In this next block, we're going to have 2 times negative 5i, which gives me negative 10i. If I look at my next block, I've got 2 times a positive 5i, which is a positive 10i. And then I have 5i times a negative 5i, which is going to give me negative 25i squared. And one of the things you also want to remember with complex numbers is that I is the square root of negative 1. And if I have I squared, that means I'm essentially squaring the square root of negative 1. So the square and the square root undo itself, and I squared then is equivalent to negative 1. And that's important because that makes negative 25i squared the same as negative 25 times a negative 1, which becomes a positive 25. So if I add all those terms together now, and if you FOIL, these are all the terms you would get, notice that my 10i and my negative 10i cancel each other out. So ultimately, I am left with 4 plus 25, which is just 29. And that should happen every single time. Whenever you multiply a complex number times its conjugate, you're going to get a real number. So in this last bullet, it asks which values of a and b would yield a real value for this quantity. And so you have to remember the relationship between a complex number and its conjugate. When we multiply them together, we get a real number. So that must mean that these two quantities are complex conjugates, which means that these terms need to be the same. So a must equal 4. And if these are going to be complex conjugates, that means that these terms, the term involving I, has to be opposite. Well, I already have the opposite sign, so that must mean that b is equal to 3. And that will make them complex conjugates of each other. And when I multiply them, I will get a real number. Okay, number 9. This is a problem that was very similar to one of the ones you did on your first marking period assessment. So you're told, suppose f of t, and I think actually this question might have been on the review guide that we did, but suppose f of t is equal to negative t squared plus 12t plus 2, and that represents the height in feet of a water balloon being tossed in the air, where t represents the time in seconds. Before I do anything else, let me go ahead and draw a picture of this. So here is my time in seconds, and we're talking about the height, so that means my y-axis is the height. And I'm talking about throwing a water balloon. And notice that the equation is quadratic. That means that the graph is going to be a parabola, and since the leading term is negative, that means it's got to be a parabola that goes down, and that makes sense. When you throw something up, it's going to come down. So here's my water balloon. Okay, so this is my balloon. Okay, and the next sentence says, let g of t equal 6t plus 2. Now that's a linear equation. That's in slope-intercept form. And that represents the height of a rock being propelled from a slingshot toward the balloon. All right, so let me just go ahead and draw a straight line. And I don't actually need the axis because I'm not really sure where these graphs cross the x-axis. But let's make that the the height of the rock. Now, eventually the rock is going to have to come down. So notice that it says the rock follows a linear path for the domain of 0 to 8 seconds. And that makes sense because just like the balloon, the rock has to come down. But at least initially, the rock is pretty much following a straight line path, and then eventually it's going to come back down and fall to the ground. But at least up until 8 seconds, it's straight. And so that's all that it's saying. It's just saying that for a certain amount of time, the path of the rock looks like a straight line. It's not going to defy gravity and keep going. Obviously, it's going to have to come back down. So what I can see from the graph is that there are two places where these graphs intersect. They intersect here at probably around t equals 0, which would be where they're both being launched. So this would be the initial launch. And then this point here is where they hit, or where I hope they would hit, and the rock would actually pop the balloon. And so the question is asking, at what time after the initial launch does the rock hit the water balloon? And so I am trying to find this point of intersection. And we actually learned this in our systems unit. If I want to find the solution to a system, I just have to find where they intersect. And I can use the substitution method. Since both of these functions are equal to the height, I can set this quantity equal to this quantity. So we have negative t squared plus 12t plus 2 is equal to 6t plus 2. Now notice that when I put these two things together, it still is a quadratic equation. It's just it's not in standard form. So just like we did in the previous problem with the discriminant, I'm going to want to scoot all of my terms over to one side. It doesn't matter which side you use. So I'm going to go ahead and move the 6t. And again, when I move the 6t, I'm going to be subtracting it from the t on the other side. And I'm also going to go ahead and move the 2. So I'm going to subtract that from the 2 on the other side. And so all of the terms on my right are going to cancel. And on the left, I'm going to have a negative t squared plus 6t. And notice that my 2's cancel on the right side or on the left side as well. So I'm just left with negative t squared plus 6t is equal to 0. Now remember, this is the non-calculator part of the test. So you do need to be able to solve this quadratic equation. And basically, my c value is 0. The easiest thing to do here is to think about the greatest common factor. So if I have negative t squared plus 6t, and that's equal to 0, I want to see if there's anything in common that I can factor out. And what I notice is that both of these terms involve a t. So that means I can factor a t out. The other thing I'm going to want to do is factor out that negative. So I'm essentially going to divide both sides by negative t. And it's just a common practice when we're solving quadratics that we like our leading term to be positive. So if I divide both sides by negative t, it's not disappearing, I'm just factoring it out. So I'm undistributing it essentially. So it's going to come out in front. And I'm going to have, because when I divide a negative t squared by a negative t, the negatives are going to cancel, and I'm going to be left with one factor of t. In the second term, I'm taking basically 6t and dividing it by negative t, and again, that's just like a negative 1t. So 6 divided by negative 1 is going to leave me with negative 6, and my t's are going to cancel. So what I have now in factored form is negative t times t minus 6, and that is equal to 0. Once you have a quadratic equation in factored form, then all you need to do is set each term equal to 0, because we have the zero product property that says if I multiply two things and my answer is 0, then one of those things has to be 0. So that means that either negative t is equal to 0 or t minus 6 is equal to 0. And so now I'm just going to solve each of those equations separately. Well, if I have negative t is equal to 0, if I divide both sides by negative 1, I'm going to have that t is equal to 0. And again, we're talking about seconds. And if I look at my second equation, t minus 6 equals 0, well, if I add 6 to both sides, I get that t is equal to 6. And again, that's going to be in seconds. So notice that I have two solutions here. Well, that kind of makes sense because there are two places where my rock and my balloon collide. There's going to be at the initial launch, and that's going to correspond to the t equals 0 seconds. And then there's going to be this point here, which corresponds to 6 seconds, which makes sense because they shouldn't hit beyond 8 seconds, since 8 is the domain for my rock. So you only want to select one of these answers, and since it's telling me the time after the initial launch, I know that t equals 0 is not going to be the solution I want. I want the t equals 6 seconds. Okay. In number 18, this is a calculator-based question, and it actually requires you to do quadratic regression. So I'm going to go ahead and set up my, sorry, I have a calculator up here somewhere. Sorry about that. There it is. Get all this stuff out of the way. Okay, now I've got my calculator. So in number 18, this is a constructed response problem, which basically means it's not multiple choice. You need to show all your work, make sure you answer all the questions. If it asks you to justify your response, you should be writing sentences. Don't forget, in word problems, you should also include units. And again, show all your work. So in number 18, it says the table below shows the amount of Jeff's electric bill during the first year in his new apartment. Assume that T is the number of months since he moved in, and C is measured in dollars. All right, so if we want to determine a quadratic regression equation, that's something I'm going to let the calculator do. But I have to enter the data into my calculator. So I've got some stuff in here already that I need to clear out. To enter data, remember data is the same thing as statistics. That's what the calculator calls it. So we're going to hit our statistic or our stat button, and that's going to take us to this menu. We want to edit because we want to be able to edit our list to enter the new information. So you can see that I already have some data in here. If you scoot to the top of the list so that the L1 or L2 is highlighted, you can hit the clear button and then enter, and that'll clear out the list for you. And I'm only going to be needing list 1 and list 2, so I'm going to go ahead and clear those out. Don't use the delete button because, well, here, I'll show you. If you use delete, it'll actually make the list disappear. It's not a big deal. If you go back to your stat menu, you'll see that option 5 is the setup editor, and if you choose that and press enter, it'll say done. If you go back into your stat menu, your list is back. So clear will clear the list. Delete will actually make it disappear. So make sure that you're using clear and not delete. Okay, let's go ahead and enter our data. So I'm going to go ahead and enter my time in list 1. And remember, time represents the number of months since Jeff moved in. And then okay, and like magic, my list is full of numbers. If you need to press pause to enter the rest of your data, go ahead. I just didn't want you to wait while I did that. Okay, so once you have your data entered into your calculators, list 1 and list 2, let me just remind you that this is list 1 and this is list 2. It says to go ahead and determine a quadratic regression equation. I'm going to go back to my home screen by hitting second mode or second quit. I'm going to clear out my home screen. And then to calculate the regression equation, I'm going to go again to my stat menu because that's where all my statistics are. That's where all my data is. And instead of entering the data in a list, now I'm going to go over to the calc menu. So I'm going to use my right arrow and go to calc. And this is the menu that allows me to do all the regression. Now you are specifically asked to use quadratic regression here. So you want to scoot down until you get to option 5, which is quadratic regression. We're going to press enter. And the calculator requires that you tell it where the data is and where you want to store your equation. So I have my X data, or my T data in this case, in list 1, and my Y information is in list 2. Now be very careful because the newer calculators also have a frequency list. This is something that you would use if you had like a frequency table, which we don't have in this case. So I'm going to use delete to clear that out. So you want to leave that blank. But what you do want to do in the next line is store the regression equation in y equals. And so, because basically I don't want to round my equation at all when I type it into y equals. I want the calculator to store all of the values there. So to store my regression equation in y equals, since y is a variable, I'm going to go to my vars button. Since y equals is a y variable, I'm going to scoot over to y vars. It's a function, so I'm going to choose that first option. And then I can paste the equation in any of these functions I want. So I'm just going to go ahead and choose y1. And now I'm ready to go ahead and press enter. And that is the equation you should get. Now, if you have an older calculator that doesn't prompt you, then essentially you're going to be entering in this command. So you're going to do quadratic regression list 1, comma, list 2, and then you're going to do the same thing that we did where we went to vars, y vars, function, and you're going to choose y1. But instead of entering it in the menu, you're going to enter it as a string of commands. Some of you might also see an R or an R squared, and that's fine. You can actually use that in the second bullet. If you don't see an R, well, let's go ahead and write the equation down, and then I'll talk about what that means. All right, so the quadratic regression equation, you can see that the calculator produces this in standard form. You want to make sure that you write at least 3 decimal places when you write the equation, and you want to make sure that you're writing the equation in standard form. Don't just copy the screen. We want to write it as an equation. So y equals, and actually in this case, we're told instead of using x and y that we're going to be using t and c. So we actually, to be consistent, should actually call our equation C equals, and then my A value is going to be 7.571. And so instead of writing x squared, I'm going to write t squared. And then minus 101.55. Now, since the next to the 0 is a 7, I'm going to want to round that 0 up to 1. And again, I'm going to use t. And then plus 439.11, and again, since the 9 is next to the 0, I'm going to round that 0 up to 1. Okay, so there's my equation. In the second bullet, it says, use the model to predict the cost of Jeff's electric bill after 16 months. Does this estimate seem appropriate? Use mathematics to justify your response. So let's go ahead. There are several different ways that you can evaluate the function at 16 months. If you want to construct a scatter plot, for example, you can look at the graph, and there's a way to calculate it there, or you can use the table. So if you go to second graph, that's where your table menu is. You may see something like mine where you have just a couple of x and y values. The screen could be blank, or it could be filled with numbers. So if we go to our table set, notice above the window button, there's a table set feature. If you want the calculator to give you a table of values automatically, you can set both the independent and dependent values to auto. But if you just want to enter in a couple of x values, sometimes it's easier just to set the independent variable to ask. And that's kind of what I want to do here, because I just want to evaluate the equation at 16 months, and I don't want to have to scroll all through my table. So set your independent variable to ask, and let's go back to the table. So I am simply going to enter in 16 for my x, or in this case, my t variable. And the calculator is going to report the corresponding y, or in this case, c. And if I'm using function notation, I can actually call this function c of t. And what I just computed is c of 16. And that would be the proper mathematical way to write it. And what my calculator predicts when I plug in 16 months is that the electric bill, and let's make sure we're continuing to use the context of the problem, that the electric bill is going to be $752.52. Now, I know many of you probably don't pay your parents' electric bill, but we can sort of see if we look at this time period, we're going from 3 to 9 months, which is not quite a full year. But I can see that my values sort of rotate between, about $80 and $200. So the highest it is like $194. The lowest is about $80. And that's typical of electric bills. They're going to go up and down with the season. So something like 752 should seem a little out of whack with the values in the table, even though as my t values increase to 9, these numbers are also increasing. One of the things that we want to keep in mind is we only have data for these months, for months 3 through 9, and we're making a prediction at 16 months, which is pretty far beyond the data in my table. When we're modeling using real data, our model is really only appropriate for the data that supports it. We can make predictions for maybe 10 or 11 months, but if we go much further beyond that, I lose confidence in my estimate. So that's kind of what we want to respond to here. 16 is well beyond the data in our table, and so we really don't have a lot of confidence in our model beyond that. And so even if it's a great model, and so that's what I'm going to write in words. Since we only have data through 9 months, I'm not very confident in this estimate or prediction because 16 is so far beyond my table. Oops. You could also say that, $752 for an electric bill that seems to be between $80 and $200 seems very inappropriate. And so, yeah, I can maybe add that here. This seems very high. And this, when we make predictions that go well beyond our table, we call this extrapolation. And in statistics, that's something that's very dangerous. We want to be really careful not to put too much confidence in our model beyond the data that we have that supports it. And then in the last bullet, this is something that's on the honors exam only. It says that Jeff's friend claims that the function f of x equals negative 29.65x plus 281.44 is a better model for the data. Justify whether Jeff's friend is correct using mathematics to support your answer. Well, what I can see from the data is that it changes direction. Initially, the electric costs are going down, and then they go back up. Well, Jeff's friend's model is a straight line, and I know a straight line is not going to change directions. But to be sure, what we want to do here is look at the graphs. And so here I really do want to set up a scatter plot. So if you go to second y equals, what we want to do is turn a scatter plot on. And so I'll notice that the very first option where it says type of graph is the scatter plot. Then you want to make sure that your x's are coming from list 1, your y's are coming from list 2. And now I can just do zoom statistics or hit zoom and the number 9. And what you should see is the scatter plot along with your parabola, because that's your quadratic regression equation. And I can see, that's a reasonable model for the data that I have. Let's go ahead and also add in Jeff's friend's model. So let's go into y equals. And I don't want to make my original equation disappear. So I'm going to put Jeff's friend's model in y2. So that's negative 29.65 x. In this case, it should be t, plus 281.44. Okay. And once I have that equation, I can go ahead and graph again. And so if you look at the two models, I think it's pretty obvious that Jeff's friend's model doesn't follow the pattern of the data. Since it's a straight line, it doesn't follow the direction change in the graph. So if you are going to be referring to a graph to answer this question, you want to make sure that you have a sketch of it. So since I am going to refer to the graph, I've got my original data, and I'm just sketching it. It doesn't have to be perfect. So that is the electric data. So here is the time, here is my cost, and then I'm going to draw this is Jeff's model. And then I have his friend's model, which looks like this. Okay, and so you want to make sure that you say something here, in this case, to talk about the change in the direction. So since the electric bill, decreases and then increases, and I'm going to say as shown in the table and the graph, a linear model would be inappropriate. And actually, I'm going to refer to Jeff's friend's linear model. And that's because it doesn't follow the trend of the data. And I'm even going to say the curved trend in the data. Okay, so again, if you're going to be referring to a graph, then you should include the graph on your paper. And notice that it's asking to use mathematics to support your answer. One of the things you could also do is use both equations to make a prediction. So for example, at 9 months, I could use Jeff's model to predict 9 months. And so if we go back into our table, if I go to second table, you're now going to see two columns of Y data. Y1 is going to refer to Jeff's predictions, and Y2 is going to refer to his friend's predictions. So if I type in a 9 here, I can see that Jeff's model predicts $138.42, which is very close to the actual cost of the electric bill. But if I look at his friend's model, his friend's model predicts $14.59, which is really, really far away. So that would be another way that you could use mathematics to support your answer, would be to maybe look at several values, several predictions. In fact, you could even continue the table this way and say this is Jeff's predictions, and this is his friend's. And then if you wanted to, I can also show you, if you go back to your table set, since our table starts at 3, I could set my table start at 3, and then the change in table, since my t-values are just increasing by 1, I could change it to 1, and then change everything to auto. And so now if I go back into my table, I'll have complete lists. So you can actually compare a bunch of these numbers, and you can see that initially both functions are relatively close, but as you get closer to the 9th month, you can see that while Jeff's model is going to stay fairly close, his friend's model does not. So, I mean, if you wanted to, you could continue the table here and have Jeff's predictions and then his friend's predictions. I wouldn't waste a ton of time since you are limited in how much time you have for the test. One of the things you do want to consider are those time limits, because you're not going to get any extra time on the midterm. So focus on doing the problems that are worth the most points first, but don't spend a ton of time. If you have time at the end of the exam to come back and work on those problems, that's a good idea, but don't spend a ton of time filling in complete answers for something that's only worth 1 point. Okay, so that concludes the quadratic section of the review packet. I hope this was helpful. Obviously, if you have questions, you can talk to your teacher. The next 2 videos, I'll have a video on polynomial functions and then another that covers all of the sequences, exponential, and log functions.